Our goal in this project is to achieve safe vehicle control in dense urban environments, specifically with game-theoretic planning. One common approach to doing so is using single-shot model-based action generation, for example with the intelligent driver model. While this is fast, it is difficult to make models for dense environments where interaction dynamics are extremely important. This can be improved upon by planning over a time horizon using predictions of other vehicles' motion, but this fails to take into account how the ego vehicle's action plan will affect the plans of other agents. Game-theoretic planning addresses this latter problem. Though recent advancements like ILQ games and all games have made computing Nash equilibria plans more tractable, game-theoretic planning still scales extremely poorly with the number of agents, as can be seen through the table on the right. Our work addresses the scalability issue in a dense environment by delegating the computation of game-theoretic plans to strongly connected components of an interaction graph. We leverage the fact that not all agents in a scene realistically observe one another, so games should be played between clusters of agents who do, with outgoing observations imposing additional constraints based on predictions of the observed vehicle's motion. For example, in this scene, we observe 3 agents who mutually observe one another, and a 4th agent who they observe but who does not observe them. So the 3 agents play a game together with additional constraints to avoid collisions based on predictions of the 4th agent. On the right, we show the resulting local equilibrium plan for this scene, with the first 3 agents accelerating towards their target velocity while avoiding each other and the 4th vehicle. In our experiments, we compare our approach to fully centralized game-theoretic planning, as well as a baseline which uses an adaptation of the intelligent driver model for action generation. For our game-theoretic planning, we use all games to generate open-loop local Nash equilibria plans, which are then wrapped in model predictive control. Each player's objective is to target a velocity while minimizing control effort and avoiding collisions. We use the interaction dataset to fix vehicle paths and spawn times in real roundabouts. Here, you can see a simulation with our approach on the left compared to the IBM adaptation on the right. In general, we find our approach to generate collision-free, human-like merging behavior. You can see instances of vehicles slowing down or speeding up to safely merge into traffic or to maintain safe distances. Our method also outperforms a fully centralized game-theoretic approach, where the number of agents can limit the solver's ability to generate safe plans.